Welcome everyone. My name is Linda. I'm a children's book author, probably the first children's book author ever to address this conference. I'm a programmer, I'm an illustrator, and I'm a business school dropout. The reason I'm talking to you today is that I believe that this is the thing that makes us humans special. We can be many things at the same time. Computers are binary. They can be one thing or the other, ones or zeros, or on or off. But as humans, we contain multitudes. We can be many things at the same time, and that's what makes us special. I co-founded an organization called Rails Girls that teaches young women programming all over the world in over 270 cities. I come from a very small country next to the previous speaker, President Ilves's home country. I come from Finland, and the goal of Rails Girls was to introduce the fun and whimsical world of programming and computers for young women all over the world. This is what I believe in. I believe that if programming and coding is the new universal language, we ought to be teaching poetry classes instead of grammar lessons. And what I mean with this is the idea that programming and technology are starting to be such immensely important tools that shape our reality. And we need a more diverse group of people to be excited and see a lot of the possibilities that this language offers. Religions don't shape the everyday life of billions of people. Governments don't shape the everyday lives of billions of people. But Facebook and Google, they shape lives of billions of people, and that's why we need more diverse people to be part of building those solutions. And in the same way, we don't teach Korean or English only by going through grammar lessons, only by practicing different grammar rules. We learn a natural language by speaking it. In the same way, we need more diversity in the ways we teach programming and technology. So I decided to write a book about this. When I was learning programming, I was practicing a programming language called Ruby. And every time I would run into something that I quite didn't understand, like what is object-oriented programming or what is garbage collection, I would try to imagine how a 6-year-old little girl would explain these concepts. And that's how the story of Ruby became. Because stories, after all, are the way we learn about the world. They are the way we learn about ourselves, and they are the way we learn about each other. But for some reason, the world of storytelling and the world of technology haven't collided in the past. So the book became very popular. It raised almost $400,000 on Kickstarter when it was first introduced. And today it has been translated into over 23 different languages, including Korean. And some of you might be thinking, why a book about programming? And in some ways, I feel like books are something we people understand. They are a campfire we can gather people around. And I've started to realize that after all, my work is not only about teaching kids about coding, it's about preparing them for a future where all problems are looking like computer problems. And that's a pretty bold statement to make. But I truly believe that every single problem in the universe will be a computer problem. But the brains that are going to solve those problems are not going to be the brains of only the current engineers. We need more diversity in the thinking skills of the people who know how to use computers to solve the big, hairy problems of the world, those of education, of energy, of nutrition. And where else to start than the kids? I think we didn't know how important technology is when we first started to teach technology for kids. And technology is far too important to be left only for the technologists. I think we need equity and equality in the way we teach technology education for our kids, so that the little girl who gets excited about learning through singing has a chance to see the magic of computer science, so that the little boy who learns best by illustrating and drawing will have a chance to fall in love with computers. And I think it goes also beyond gender. I think little girls are amazing with computers. They are so good at concentrating. They ask wonderful questions. They know how to solve difficult puzzles, and they don't know that they are not supposed to like computers. It's often us adults who move our own perceptions about who is allowed to touch computers to our kids. the little kids don't know yet. So, to make this world more approachable and to tell a story around technology education that ought to be told, I invented this character called Ruby. Ruby is like any 6-year-old, imaginative, fearless, a little bit bossy. And when Ruby's dad tells her, "Ruby, we should go to school. You should dress up really quickly. We're running late." Ruby, she does dress up, but she leaves her pajamas on because Dad didn't first specifically tell her to take the pajamas off. And when Ruby is told, "Oh, Ruby, your room is a mess. Please clean up all the toys." Ruby cleans up the toys, but she leaves the pens and papers on the floor because, "Dad, pens and papers are not really toys." And there is a chance I'm raising the most obnoxious generation of kids ever. But they also learn something truly profound about how to speak to a computer. Namely, that you need to give very exact commands. The commands need to happen in the right order. You need to be careful when naming things. You need to take into account all kinds of different situations. And then finally, and most profoundly, that even the biggest problems in the world are just tiny problems stuck together. And this is the thing I'm most jealous for computer scientists. Making computer science approachable for all kinds of learners requires us as computer scientists to ask questions we haven't asked before. It might include asking questions like, how does a loop feel, instead of trying to explain just kids what a loop is. So a loop is a construction in computer science with the idea that a computer is really good at repeating sequences of instructions over and over and over again, but it needs exact instructions to do that. And in Ruby's universe, we might practice the concept of a loop by having a dance party. Ruby's favorite dance sequence is this. She likes clap, clap, stomp, stomp, clap, clap. And with the kids, we might practice different kinds of loops by having a physical, actual dance party. So we might practice a for loop by repeating this sequence of dance movements 5 times. We might practice a while loop, which is another type of a loop, by repeating the sequence while I'm standing on one leg. And then finally, we might practice an until loop by going home and repeating this dance sequence until mom gets really, really frustrated. And in this way, the kids will have a very kinetic, very physical, very non-abstract idea of what a loop is, first by experiencing a loop, then maybe taking a visual programming language like Scratch, and only then starting to write the syntax, the code of what a loop looks like in JavaScript or Ruby or Python. And then, very importantly, I think our educational systems should give context for all of this learning. So instead of just teaching kids these abstract concepts of computer science, we should teach them, where do you see these in practice? So for instance, when you're playing a video game, there is a loop that says that keep repeating, keep moving the hero onwards until it hits the enemy. Or if you log into a website, there's a loop that asks you to write your password 3 times before it locks your account. And in this way, we give kids an experience what it feels like to write code. Because for a lot of us, code looks like the code you see on the right-hand side, the assembly code of the 70s, and it looks very frightening and scary. Luckily, programming has become much easier in the past 30 years, and modern programming languages, at least to me, they look more like poetry. They look like English, and it's much easier to write code than it was, say, 20 years ago. And a lot of people are really frustrated when they run into programming languages and they realize, oh wow, there are so many that I need to learn. The good news is that there are similarities across different programming languages, so you don't need to learn a new language from scratch. Even though you would have never seen any programming language before, looking at these 4 pieces of code, you can kind of spot similarities across the pieces of code, thinking that, oh, there's these parentheses that hold items together. There's the word length, that's a function that calculates how many items inside of the parentheses. And in this way, I think we can make computer science approachable for all kinds of learners. The thinking skills behind these topics are called computational thinking skills. And I think there's a difference between teaching coding skills to kids and computational thinking skills. Coding skills get outdated really fast. Programming languages change quickly. But the thinking skills behind the syntax, computational thinking skills, that allows us humans to give exact instructions for a computer, they will stay for a long time still. And they include things like pattern recognition skills, logical and critical thinking skills, algorithmic thinking skills. But more importantly, they also include practices like persistency, creativity, collaboration. And combining the concepts with the practices will give us a future generation of coders. But the programming languages aren't enough. The computational thinking skills aren't enough. In order to really equip our kids for the future, we also need to give them a really robust understanding of what computers are. And I love computer scientists, but they've done something horrific. In the past 20 years, they've built layers of abstraction on top of each other so that we as consumers don't need to care about how computers work anymore. For everyone here who was born in the 70s or fiddled with computers in the 70s, I'm a little bit jealous because you could actually touch a transistor. You could actually see what a transistor looks like. For my generation, a generation of the 90s, there's 300 million transistors on top of a pinpoint of a pen. And there's no way of understanding how a computer works anymore. They've become too abstract and too closed. Sometimes I wish I could shrink myself to the size of a silicone chip and learn how a computer works by walking inside of one. But unfortunately, that's not possible unless you're a children's book author. So that's exactly what I did with my Ruby. One day, she's very bored, and she goes into Dad's office, and she types her password into the computer, but the computer doesn't work. And the white mouse wakes up to Ruby and says, "Ruby, Ruby, I've lost touch with the cursor. Can you help me debug this problem?" And Ruby says, "Of course, happily." And together, they fall deep, deep inside of the computer to the layer of the electricity. And they meet the bits, the tiny switches that only know how to go on and off, that power the entire computer. And they realize that the bits are not going to be much help for us. We need to climb higher. So they meet the logic gates that combine these bits in different ways and pose funny questions for Ruby, but they are not much help either. They meet the hardware layer of a computer and the CPU that is really good at giving instructions for all of the other components, but bad at remembering things, so it needs help from the RAM and the ROM and the hard drive. And they meet the operating system that hides all of this complexity from us. And I'll spoil you a little bit, they also meet the mouse and the cursor eventually, but I think more importantly, the kids get this very beautiful experience of what a computer is from the lowest level of abstraction all the way to the programs and apps we use every day. And they realize that a computer can take 1,000 forms and have 1,000 functions. Today, computers are digital, but maybe tomorrow they are theoretical, biological. We don't know what a computer of the future looks like, and that's the future we need to educate our kids for. One of my favorite exercises to do with kids is this one where I ask them to imagine what is inside of a computer. And I bet if I asked all of you to imagine this question with me, most of you would say, "Oh, I don't have a PhD in computer science. I can't know what happens inside of a computer." But the beautiful thing about kids is that they venture out and they make a hypothesis. So sometimes kids draw illustrations that describe computers as containers of content, computers that store apps and files inside of them. Sometimes kids draw computers that have these interlinked networks of components. They think like computer architects. Sometimes kids explain that the computer is a theater stage where different components and functions come to meet. That's a beautiful analogy. Sometimes kids imagine that inside of a computer there's thousands of little gears that work. It's kind of this steampunkish way of seeing a computer. And then there's my favorite kids. The kids who try to draw out different transistors and different components. The kids who kind of get a grasp of the electricity layer of a computer. And the kids who most importantly understand that while a computer is magical, it's not based on magic. A computer is not based on magic, It's based on logic. The next step in this exercise is one where the kids get to build a computer. And instead of building an actual computer, they actually build a computer out of paper. And they assemble their computer and they get to know the different components and they start to create applications for their computer around the age of 4 or 5. And I've seen some wonderful, whimsical, fun applications that the kids create. But one of my favorite stories is a story of a little boy who's very proud of the paper computer he created. He has these huge headphones on his head, and he's completely immersed in his computer. Because you see, he has built an intergalactic planetary navigation application. And the boy's father is a lone astronaut on the other side of the room, but really far, far away in the Martian orbit. And the boy's role is to bring dad safely back home on Earth. And I think kids who grow up having this kind of a relationship with technology are going to have a profoundly different view of what it means to create with technology. Because the challenge is this. We are the last generation that remembers computers as glowing boxes, computers as defined by screens. The next generation of kids will have embedded computers everywhere around them. So I start with the 5 to 9-year-old kids often with this exercise, where I show them a picture of a car, a picture of a grocery store, a picture of a toilet, and a picture of a dog. And I ask the kids, which one of these is a computer? And the kids, who we think are so creative and fearless, they all cross their hands and say, Linda, are you totally bonkers? None of those is a computer. The computer is the thing mom or dad spends way too much time in front of. Oh. But then we talk, and we realize that actually a car is a computer because it has a navigation system built inside of it. Grocery stores have hundreds of computers because a teller's machine is a computer. The ice cream box that keeps the ice cream cold is a computer. The burglar alarm is a computer. Dogs are not computers, but the dog's collar, it might have a computer inside of it, and that's great if the dog is prone to running away. And don't do this if you have under 6-year-olds at home, especially in the Western countries. But I tell kids that in Korea, toilets are computers, and there's even hackers who hack them, and all the kids are like, ha ha ha, what's happening? So end of discussion over there. But we realized that actually there's not 1 or 2 computers in your house. There's hundreds of computers in every single home. And the exercise continues then like this. I give all of the kids this little sticker with an on-off button on it. And I give them everyday household items like a tuna can or a pair of keys or a water bottle. And I tell the kids that, you know what, for this afternoon alone, you have this magical ability to make anything in this room into a computer by placing this little on-off button on it. And again, the kids object. They say, Linda, this is too difficult. Linda, I don't know the right answer for this question. And I tell them, you know what? Neither does your parent. They might have heard about this thing called the Internet of Things or the IoT. But you are the generation whose toothbrush will be a computer, whose teddy bear will be a computer, and it's up to you to imagine that world. So I have this little girl who comes to me with a bicycle lamp, and she tells me, Linda, if this bicycle lamp were a computer, me and Dad, we could go on a biking trip together, and then in the evening we could sleep in a tent, and this bicycle lamp, it could also be a movie projector. And that's the moment I'm looking for. Not the moment when the kid can write the perfect if-else statement in JavaScript. Not the moment when they understand the difference between hashes and arrays in Ruby programming language. The moment when they understand 3 very profound things, even as adults have a hard time remembering. First of them is that the world is not ready yet. There's so many things we haven't invented yet, like the movie projector, bicycle lamp. The second thing she realized was that technology is a wonderful way to make the world a little bit more ready, a little bit better, because it scales and it creates wealth around it, and technology is the way humankind has always advanced. And third, and maybe the most important point, is that she felt for a moment that she could be the world's first bicycle lamp movie projector innovator. And I think that kind of self-efficacy, that kind of self-belief is something we ought to be guarding in childhood and also in ourselves. So how do you explain what a computer is for the next generation? In order to do that, we need to go all the way back to the year 1945, when John von Neumann came up with his famous von Neumann architecture for a computer. And for those of you who don't have a degree in computer science, what von Neumann said is basically a computer is any device where you input data, you process the data somehow, and then the modified data comes out. And this is true when you go on Facebook and you like a post. In goes the information that someone has liked this post to Facebook server. Out comes the updated like count. But this is also true when you sit in a car and there's a sensor that recognizes that you forgot to lock your seatbelt. In goes the data that the user has forgotten to lock the seatbelt. Out comes the beep, beep, beep noise we all hate so much. The thing that makes a computer is so magical is the memory. And computers have two types of memory. They have the memory that remembers the data that comes in and the modified data that goes out. But more importantly, they have the memory where you write the instructions on what to do with the data. And this is what makes computers special. Because a tractor can only be a tractor. A pinball machine can only be a pinball machine. But a computer can be any device based on the instructions you give for it. So when we think about a computer and when we think about the future of computing, I think having these theoretical mindsets helps us understand the changing landscape. You will hear a lot of talk about artificial intelligence in the upcoming 3 days. But when you think about artificial intelligence being input, output, and process, it will make life much easier. Instead of being frightened about self-driving cars, you can think that the input for those is just car cameras and the output is the position of other cars. And this is the beauty of computing and computers. So what about the data? What about the data that goes in and is modified and goes out? I think there's a lot of things that we as adults are frightened about when it comes to data. And the kids, luckily, they are not that frightened about data. So one of the exercises I do with kids is this one where we talk about data selfies, and I give kids these logs where they start to record things they do online. They record 5 things they've searched for online, they record people they've messaged with, they record places they've been with their phones because the phones track the location you go to, and they make a list. And then they swap the list with one another. And the other person needs to think like a computer and try to imagine what kind of a persona this could be and draw an illustration around that persona. And the next step is to give the kids the front page of a local news site and block a few pictures, a few titles, and a few news stories, and ask the kids to imagine how would you modify this front page to suit the persona you just created? What kind of a newspaper would a 5-year-old boy who loves turtles and has visited Seoul and Helsinki in the past week love to see? And then we get into really interesting discussions about how it might be a good thing that everything we see online is modified to our tastes, and how it might be a bad thing. And the crazy thing is that the adults don't know this reality exists. When I told about this exercise for my mom, who's almost 60, she said, "Oh wow, is that why Facebook knows how to show me the exact ads for the dress that I was browsing earlier on?" And I go, yeah, that's an algorithm, and that really powers the things you see online. I think in the future, kids should have a really robust understanding of what a computer is good at and what a human is good at. And this is far more important than teaching them to mechanically be able to write code. And one of the ways we practice this with kids is through an exercise I like to call the art machine. So to start this exercise off, I give each kid an algorithm. For us adults, an algorithm is a scary big word. We think about Facebook and we think about finance, but kids really like the word algorithm. It's big in their mouth, it seems very adult. And the kids know that an algorithm is just a step-by-step sequence to solve a problem. Nothing fancier than that. So an algorithm might be to draw a green circle, or an algorithm might be to always draw a red dot inside of a green circle, or an algorithm might be to connect the red dots with a green line. And I turn this art machine on, and each kid starts to execute their algorithm on the paper. And in roughly 20 minutes, we've created this beautiful piece of work. And we stand up and we look at the work and we go, this is pretty cool. We feel proud about ourselves. And I ask the kids, so how long do you think it would take a computer to create an artwork like this? And the kids who are roughly 5 or 6 year olds, they count. There's 10 of us, and it took us 20 minutes, so probably it would take 200 minutes for a computer to make this. And I tell them, you know what? A computer could probably generate 100 million of these in a nanosecond, because this is exactly the type of task a computer is good at. A computer is good at repeating instructions and sequences of instructions over and over again mindlessly, faster than any human being. But how does this artwork make you feel? And a little girl comes forward and says, oh, Linda, it makes me feel very busy. And another girl says, oh, it makes me think of last summer. And I tell them, so this is the thing computers can't yet do. They can't experience their own emotions around art. They can't offer an interpretation on an artwork based on their experience. They can go to Wikipedia and maybe show that this looks like abstract painting, but they can never offer an interpretation based on their own experience. And these are some of the things that us humans will be better at than computers for a long time to come still. And maybe the kinds of professions where you need skills like empathy, where you need to do things for the first time, where you need to motivate other people, are things that will remain with us humans for a long time still. Finally, the title of my talk is 100 Languages. And some of you might have been thinking that the thing I meant was programming languages. Well, no. The title is actually a poem from a tiny Italian town called Reggio Emilia. And it's a poem from the 40s or 50s when this town realized that after the world wars they had completely wrecked a whole generation of kids. And they needed to reinvent schools to better suit the future of mankind. And they came up with a poem to describe the kind of school that they wanted to build. And the poem states that the child has 100 languages. The child has 100 languages of listening, of sculpting, of painting, of drawing. I think of programming, if programming had been a little bit easier. But so often we adults take away 99 of those languages and say that you have the language of writing and reading. And I think in order to raise kids for a future where coding and technology is everywhere around us, we need to start thinking about programming as a language of self-expression, as a language of problem solving that kids can use in addition to the many, many other languages they have in their everyday lives. Just like Legos, just like crayons, just like building blocks, they can use programming as a tool of self-expression and a building tool. None of this is really new, because the history of programming is full of these multidisciplinary humans that were definitely not binary, one or the other, programmer or non-programmer. Actually, the first programmer of the world was a lady called Ada Lovelace, and she was the daughter of a poet, Lord Byron, and a mathematician mom, and she lived in the Victorian era England. And Lord Byron had a lot of affairs. He was a very womanizing man, and Ada's mom was really angry at him and said, none of that poetry nonsense for my daughter. She's going to have a rigorous mathematical education. So Ada did receive quite the mathematical education for her era of a woman, but she also kept a little bit of that poetic mindset of her father's. So when Charles Babbage was building the first computer in the Victorian era England, the analytical engine, Ada was the person who realized that it's not a calculator we're building. Ada was the first person to realize that actually with numbers you can represent logic, And with logic, you can represent anything in the world. And that's why we think that she's the first programmer in the world. The roots of programming are in poetry and math. Somehow we tend to forget this. Somehow we have this very binary idea about the world where, on the other hand, there's the people who use technology and build with technology, and then on the other side are the people who just consume technology. But technology is built on humanity. Technology, at its very core, is about us humans. A computer used to be a profession for people who were calculating long series of numbers. So the first computers in the world were humans. And in some ways, I believe the last computers in the world will be humans too. And we don't know what the technology of future will look like. Today, we think technology is a computer. Yesterday, it was a combustion engine. The year before that, it was a bicycle. And we don't know what the future of technology will be. But we do know what the definition of the word technology is. It comes from Greek, and it means the tools to solve a problem. But again, not only the tools, but also the attitudes, skills, and competencies us humans bring into the problem-solving equation. And luckily, the kids remember that technology is built on humanity. I asked a bunch of 9-year-olds in Helsinki to define to me what is technology, who uses technology, and what is it used for. And I got some beautiful replies. But my favorite one is this. A little girl wrote to me and said, "Technology is electricity that loves." Is there a more poetic way of saying this? No. Technology is electricity that loves. It is used to play. I use it to have a conversation with my mom. We use a WhatsApp application. And then finally, and most importantly, people uses technology. Thank you very much. Do we have time for a few questions from the audience? Yeah? Any questions at this point? I think there's a question. Oh, there? No. The sad answer. So, I think the question was, is Ruby the best language to teach for children? I think the answer is no. Ruby was the first programming language I fell in love with. It was the first programming language that allowed me to express myself in a way that felt natural and beautiful for me. But I think we have 100 languages to express ourselves. And instead of focusing too much on the language of choice for kids, I would focus on teaching them the thinking skills that a programmer needs. So the computational thinking skills, understanding what an algorithm is, being able to decompose a problem, break a big problem into smaller pieces. And if I were to choose a programming language to teach for kids, I would probably start with a visual programming language like Scratch, or Codecademy has a bunch of really interesting tools. Something that doesn't pay too much attention to the syntax, because it's so frustrating to make syntax errors and have your whole code not work. So more on the logic side of things than on the syntax side of things. And for me, Ruby worked because that was natural for me, but I bet there's people who think best with C++ or Swift or any other programming language. I think it really depends on the kind of problem you're trying to solve.
I've got 4 sons.
4 sons.
4 sons, from 12 down to 3. And our big struggle is screen time.
Yeah.
So what are some of the lessons you've learned in getting kids kind of away from playing mindless games towards engaging with machines or computers in a way that they're actually learning to code, rather than just wasting energy?
On YouTube. I think it's a really interesting question, the question of screen time. And all of the parents here know in the room that there's very productive things you can do with a computer, and then there's very non-productive things you do with a computer. So first of all screen time is definitely not equal. There's different things you can do. And in my childhood, I'd say, like, when my parents were looking at the things that I was doing with a computer, they didn't necessarily realize how complex problem-solving situations I was facing while, for instance, learning to program as a teenager. They just saw me sitting in front of a computer doing this. So first, like advice would be to ask what your kid is doing with a computer. If they are playing Minecraft, it's a very different thing than if they are just watching YouTube videos. So engage with the kid and ask questions about what they are doing. Then the second, maybe more practical advice on how to get your kids working on actually productive and coding-related things is try to figure out the context of learning that suits the kid and a project that motivates them to learn. So for example, when I took computer science in high school, the first exercise that we were asked to do was to write a program to calculate the first 20 prime numbers, first 20 square roots of the first 20 prime numbers or something like that, which was a horrible exercise for me because I wasn't interested in math. I was interested in somehow using a computer to express myself, and that's something I pay a lot of attention to when working with kids. Finding what is something that they are interested in and then figuring out how a computer can enhance that experience or build upon it. And it's no coincidence that a lot of programmers get started by, say, building websites for their I don't know, like their online gaming community. I learned to program because I wanted to make a website for Vice President Al Gore when I was 13 years old and stuff like that. And I had, for instance, a little boy come to my classes or workshops, and his big thing in life was, like, he was very into dangerous animals, like many boys are when they are 6 or 7 years old. And he was very obsessed with this idea of dangerous animals. So we put on Google, what is the world's most dangerous animal? And Google says, a 3-kilometer-long snake. And we look at each other with the boy and we're like, is Google lying? Can that be true? So first he learns about media literacy, that like you can't trust everything that Google says. But then he's still like really excited about this idea of a 3-kilometer-long snake. So he draws it on paper and he like puts a lot of papers behind one another and he makes this long snake on the floor. But that's not quite what he was getting at. So we decided to take Scratch, visual programming language by MIT, and he programs a snake that can move on the screen, like animates his own snake. And because he's done it so well, he can now make 100 different snakes in all the colors of the rainbow. He learns about object-oriented programming. He learns about like reusable code. And it all got started from this one big passion that he had on dangerous animals. And I think that's kind of, and I don't know where the project is going to go next, but finding a context of learning and as an adult, like guiding and supporting your kid in learning those things. And then on a very practical notion, where can you learn those skills? I mentioned code.org a few times. I think it's translated into Korean as well. It's an American nonprofit that does a phenomenal job in making like accessible coding for kids. It's free of charge. You can download it. You don't need to download it, but you can use it on a tablet or on a website, and it uses all of the characters kids really love from Star Wars or Angry Birds or so forth. And as an adult, you can peek over the shoulder of your kid and learn something yourself as well. So that's one recommendation that gives kids these tools and access. And it also has a lot of other resources to try out. So many questions. Okay, wonderful. Yes.
Thank you for your speak. Finally, how old kids enjoy the computer language? Reasonable age. How old kids?
So I think we don't know the answer yet for that question. I work with kids as small as 3 or 4 years old. Up until 9 years old, but I'd say for me, like the sweet spot is 7 to 8 year old kids because their sort of logical and math and reasoning skills are far enough, and also their concentration skills are good enough. So for the smallest kids, I think their concentration is still like less than 15 minutes. But I think the earlier you introduce these concepts to kids, the more familiar and the more natural they feel for them. And especially for little girls, I'd say having role models in technology at an early age and feeling like, oh wow, this is an industry that I can belong to is very, very important. And if you start at the age of 10 to 12, they've really started to define themselves already at that age, and it's too late. So not that every kid should learn to program at the age of 4, more that I'd like kids to have this like fearlessness and curiosity towards technology and not be afraid of it, so that when later, whether it's at high school or in university, they run into actual programming languages, they would feel comfortable around them. There was one more question, I think, in the backstage. Or then maybe not. Okay, maybe final thought. Thank you all so much for coming. I know I speak a lot from girls' perspective, but maybe one of the most touching moments, especially in Asian countries, for me has been when people ask, is this a book for girls? And I say, no, it's not a book for girls, it's a book for both genders. And actually the proudest moments for me are when little boys come to me and said that, oh, like, Ruby is the favorite character in the book, because I feel that's how the world changes, when little boys can look up to girls as role models, as programmers, and that's how we'll have a better and more inclusive society. Thank you very much.